Okay, we'll get started. In this section, we're going to be looking at 5F and also 5G. So 5F being work and 5G being power. So we're going to start with the 5F section, work. So it's important to remember that energy is conserved, meaning that you can't create or destroy energy, but you can transfer it into or out of a system. Again, a system being an object. So if you had an object, you could transfer energy in, or you could transfer energy out, but you can't destroy or create energy. So the name for this transfer of energy into or out of a system is called work. And it has the symbol W. That's its variable name. So work is actually that energy that's flowing in or out of a system. Work has the standard metric unit of joules. So again, you'll see like 5J for 5 joules. Try that again, 5J for 5 joules, or like 10J for 10 joules. It has the same units as any type of energy because it really is just the transfer of energy. And the convention for work is going to be, you might see positive work and you might see negative work. So positive work meaning that you have energy flowing into a system, and negative work means that you have energy that's flowing out of a system. So an example of positive work would be is if you had a ball rolling along and then someone came up behind the ball and pushed it, gave it an applied force, and then all of a sudden it's moving faster. This would be an example of positive work because the object's gaining energy it didn't have before from an outside source. And then you could have also a negative work. So an example of negative work would be a ball's rolling along, and then all of a sudden, not all of a sudden, but it's rolling along a rough surface, so there's going to be some friction. So that ball is actually going to be slowing down. It's going to be losing energy. It's losing kinetic energy due to friction. That would be an example of negative work. So that's really work. It's just how much energy goes in, how much energy goes out. Is it positive? Is it negative? That's really what it is. Now the next idea we're going to talk about is power. Here we go. So power, which you have, it's really determining how fast work is being done. So power, abbreviated P, is a measure of how fast work is being done, or how fast that energy is being transferred. Power is going to have the standard metric unit of watts. So this W, right, that's the abbreviation for watts. So if you see like 5W, right, that means something has 5 watts of power. So the equation for power, how to calculate it mathematically, is the following. It's right here. So power is the amount of work divided, the amount of work that's going into or out of a system. So the amount of energy that flows in, the amount of energy that flows out, and then you have T, right? It's work divided by T, and T is going to be the time that it takes that work to flow in or out. So power takes into account how much energy is going in, and then also how much time that is taking. So let's give you a quick example. So let's say there was a box, and large box. Let's say you lift that box, and let's say you lift it at like a normal speed, and let's say you do 5 watts of work on that box. Sure. Then let's say you have that same box, right? You lift it in the same way, but you lift it faster. You lift it like very quickly. Then you'd have let's say maybe you had 10 watts in that case instead. And the reason for that being is that you're doing the same amount of work, but if you do it in less time, you're exerting more power on that object. So again, power is not taking into account only the amount of energy going in, right? It's not only taking into account, how heavy that box is and how high did you lift it, but it's also taking into account how fast did that action take place? How quickly were you able to transfer energy into something? So that's power. It's related to work, but it's a little bit different. All right, and I think this is going to make a little more sense once you see an example about power, work, how they're calculated, where you kind of see them in a problem. Let's go there. Here we go. So again, please read it. Please write it out. Please have your equations, and please write out your knowns and unknowns first before I go through it. Okay, so I'm going to go through this. So we have a soccer ball rolling down the field at 2 meters a second. And then Thomas Edison, at 80 kilograms, kicks the soccer ball, which is 0.4 kilograms. And the soccer ball is now rolling at 8 meters a second. And it's saying to neglect friction. So let's draw this out. We have Thomas Edison, and we have a soccer ball. So I'll just draw the soccer ball first. So we have the soccer ball by itself, and then Thomas Edison comes along. Little known fact, Thomas Edison loved to play soccer. So we have the soccer ball, Thomas Edison comes along, kicks the soccer ball, and then it's moving even faster. That's really the situation that we have. So let's think about what do we know here before we get too far into this. So we know the initial velocity of the soccer ball before it gets kicked is 2 meters a second. We know that the final velocity, so after it gets kicked, it's 8 meters a second now. We know that the mass of the soccer ball is 0.4. And we know that the mass of Thomas Edison is 80 kilograms. So A, how much work is being done on the soccer ball? So if we want to figure that out, right, there's really only one way to calculate work directly that we've seen so far. So we're going to start at the conservation of energy equation, right, the full one. UF. So that's the conservation of energy equation. So if we want to figure out how much the work he's doing, we're going to start canceling stuff up, or canceling stuff out, rather. So the work is definitely there. Initially, right before it gets kicked, there's some kinetic energy. There's really no potential because there's no chemicals, it's not raised to some height. Would assume it's just on level ground. And then in the second part, the final part of this, there's going to be kinetic, it is moving, but there's really no UF, kind of for the same reasons there's no UI. So we need to calculate work out. So we're actually going to write out, we know we can simplify Ki a little bit. We could write it out as half mv squared. Technically it's mvi squared. Sometimes we get a little lazy and don't write out the full notation, but it's really vi squared. You could just write v, but vi is a little more specific. And then it's 1/2 mvf squared because it's the final velocity squared. If you plug in now, because we really know all this stuff, we know the masses and velocities, so we can get out the work. So 1/2 times 0.4 times 2 squared is equal to 1/2 times, what is the mass, 0.4 times 8 squared. If you do that, you're going to get out the work is not equals just yet. The work plus 0.8 is equal to 12.8. So we're going to get work is 12 joules. So it's basically saying when Thomas Edison kicks that ball, he's adding kinetic energy to it, and he's actually adding 12 joules of kinetic energy to that ball. The second part is dealing with power. So it's asking him how much power is he exerting on the soccer ball if it lasts 0.15 seconds. So now we know some time. We know the time that this kick is taking place, or how long it takes to take place. So to calculate the power, we're going to do the power is equal to the work over the time. So we know the work, we know how much energy goes in, and we know the time. So the power is going to be the work, 12J, 12 joules, over time. It's what, 0.15 seconds? So if we just divide 12 joules by 0.15 seconds, we're going to get out 80. And the unit for this is going to be W for watts. So Thomas Edison is exerting 80 watts of power on that soccer ball. So that's the problem. Again, really dealing with work and also power. Looks like a lot, but not terrible if you're careful, if you write out all your knowns and unknowns. If you draw a picture, if you're careful with identifying which equation is probably going to be the most useful. So those are those two sections. So again, make sure you have the notes copied down. Make sure you have this problem solution, and that's it for now.